ICP, which stands for inductively coupled plasma, and the back ends that it can be attached to, which are OES, which stands for optical emission spectroscopy, and MS, mass spectrometry, which is what we're going to talk about in the next section. So, the advantages of ICP. It's 2 times hotter than combustion, so for flame AA we talked about 2,500 degrees. This is 6,000 to 10,000 degrees Kelvin, so very, very hot. So this is, the reason it's called a plasma is because, you know, when you can't differentiate between a liquid and a gas anymore, it's called a plasma, that fourth state of matter. Well, that's what we're dealing with because it is very hot. So you have high stability. The plasma is very stable once you get it up and rolling. A relatively inert environment because you're going to make it out of argon, which is pretty much unreactive in general, although we'll see that there are issues with that. And you can get extremely low detection limits, down to the published values are somewhere in the range of 1 to 5 parts per trillion, so very, very low. Alright, so the ICP part is how you get the sample introduced. You get the sample to the plasma. So basically what we have going on is that you have your sample is injected into the nebulizer. It hits a piezoelectric crystal that helps aerosolize it. And then you have this argon gas that can take it up into the injection, capillary injection tube. You also have a drain in case there's any that doesn't get aerosolized. And then you have plasma gas, argon gas that's going to the plasma coming in. It sweeps up the sample from the capillary injection tube. And then you also have argon coolant gas coming in. Then you have the RF radio frequency coils working at, I don't know, somewhere in the megahertz range. And that's how you get a plasma. So the plasma is like a sea of electrons and argon and sample. So there's just all kinds of business going on there. So now let's talk about the back ends. How can you use this? So you can use it for optical emission spectroscopy, just like what we talked about for the the atomic emission spectroscopy. So you have your same plasma, you generate your plasma the same way, then you have the light, the emission from when you have excited atoms going back to ground state, and then you have it coming in, getting it collimated, going on to something called a CID, which is charge injection device, which is similar to a CCD, only way better. It's a 2-dimensional, you collect data in basic, sort of like 3 dimensions. So you have 1 dimension, which is wavelength, so that's how you know what emission line you're looking at. You can also have different diffraction orders. When we've talked, I guess we haven't talked too much about Bragg diffraction, but basically there's different diffraction orders depending on how it gets bounced off. And then you also have an intensity component for each. It looks like a bunch of different spots. You can look up what the display actually looks like, but it's a bunch of different spots, and so you have an intensity of those spots. So that's how it works. So couple plasma, the ICP, with a mass spec on the back end, and I know that doesn't mean very much to you at the moment, but basically a mass spectrometry separates on the basis of mass to charge ratio. So basically you have the plasma and you have a bunch of ions coming from sample ions coming from the plasma. You sip, you sort of the cone collects only a little bit of those, and then you collimate it, focus it, get it ready to go into the quadrupole mass spec instrument. And so it's not photons that we're detecting this time, but actually mass to charge, or different ions ions with different mass to charge ratios. And so then that impacts the detector, and that's what's detected, and that's what's measured. All right, so just like with anything else, things can go wrong. So what we're looking for mostly with mass spec is isobaric interferences, where you have argon plus from the plasma reacting to form argon plus hydrogen, oxygen, carbon, nitrogen. And these can all be detected as analyte if they have the same mass to Z ratio as something that you're interested in. So a common example is a lot of people are interested in iron, But if you have argon 40 and oxygen 16 that are going to be detected all at the same, they have almost the same mass to Z ratio as iron 56. So basically, the way that you can resolve this issue, and I totally intended that pun, I'm so nerdy, is you can use a high resolution instrument, but most of us don't have access to one of those. These instruments are very expensive as it is, so a high resolution instrument, there aren't that many around. So instead, what we do is we do things like we measure isotope ratios. So what's the ratio of iron 54 to 56? And we know those ratios from the periodic table, or people have figured that out. So you can tell if you have some isobaric issues going on. You can also use a reactive gas to try to transfer electrons and hydrogen or protons away from the argon in an effort to keep that minimized. So that's basically how that works.